biological health records. And just to give you a little bit of background on our speaker today, Dr. Jiang is the Associate Vice President of Medical AI at the University of Texas Health Science Center at Houston, UT Health. He holds the position of Department Chair of Data Science and Artificial Intelligence and is honored to be the Christopher Seraphim Family Professor. Additionally, he serves as the Center Director of Secure Artificial Intelligence for Healthcare, SAFE, in the McWilliams School of Biomedical Informatics at UT Health. He was an associate editor of BMC Medical Informatics and Decision Making and serves as an editorial board member of the Journal of American Medical Medical Informatics Association. My apologies.
I feel really bad because
But I have one more line. His expertise is primarily in health data privacy and predictive models in biomedicine. So please, everyone join me in welcoming Dr. Jiang.
Thank you so much, Khadija, for the nice introduction. So thank you for joining me. And then today I had the pleasure to present our recent work just get published in EMEA this year. It's about the identification of a structured EHI using machine learning technique. So this is a work for REDX-RED. And we all know, like as a data generation group or data coordination center, one of the common tasks is to ensure the patient privacy. So oftentimes we require the centers or data generation groups to de-identify the data. So the data de-identification can be a very tedious process and error-prone when this is conducted manually. And oftentimes, even if you conduct it, they need a second verifier to check whether there are any potential missing elements. So this requires a lot of attention and should be done with the highest level of cautiousness. So we're trying to come up with a method to optimize this process and allowing people to use these tools to speed up and then improve the efficiency and efficacy of data preparation before submitting to the data coordination group. So in this particular work, we're actually proposing machine learning-based PHI fields detection, and then once it's detected, then you can design rules to do the mitigation. I was just the first to cover a few early works conducted in the REDX-RED group. So, one of the very basic idea is following the common data elements. We ask each team to submit the data and then doing harmonization with privacy protection in mind. So the group has provided a number of ready to use and then downloadable tools, including ID generation, zip code truncation, data shifting tools. So those are like local tools. You can load a database or CSV file, and then given your local ID, we will use a seeded hash function to generate a different ID and then replace the original one, and also do the truncation of dates and then shifting, so that make the data de-identified before sharing. And so you can introduce like a random dates during this shifting process so that the data cannot be directly recovered, and then so you mitigate this kind of linkage risk. And then per HIPAA privacy rule, this is the safe harbor mechanism. We need to remove a total of 18 identifiers, including like an explicit identifier like name and all the dates, and then telephone number, zip code with a region of residents less than 20,000 people, and then biometric and additional information. So imagine if you have a lot of fields and then thousands of columns, how can you quickly identify if there's any existence of these attributes in your data before you submit, right? And then sometimes it could be like a erroneous entering or other kind of condition, mistakenly added like sensitive fields in columns that shouldn't contain those. A simple technique is using regular expression. You throw in these templates and see if there's any potential match, right? So you can create a very, very complicated and sophisticated regular expression to match email address and zip code and dates and all kinds of entities. However, deterministic approach always have limitation, right? Because there are different variations, right? So like phone number and the social security number, zip code, they all have different format, and then even spellings and those things could be mistakenly spelled, but still people can infer that's like a unique identifier. And there's so many ways of express the same entity. So we think, what about using machine learning to detect those PHI from the structured data? So this is not like a classification problem, just say entry is containing a patient, the patient has some outcome. This is looking at each column to make a judgment whether there are any containment of potential risk information or unique information that could lead to privacy leakage. So detecting sensitive information requires feature engineering. So basically, because people can put gender, male, female, 0 or 1, race can be also coded in different way, right? And then birthday can be spelled in put into different structure, and then string data can sometimes also contain PHI information. So we need to come up with a method to convert those into some measurable mathematical measurements so that we can use model to come up with probability to inference. And then the most important thing is the uniqueness, right? So think about like a privacy risk. It's the uniqueness of the data that lead to re-identification, right? Name is unique, social security number is unique, MI is unique. So all these things that have a high likelihood of being unique, or combination of these things who can lead to unique linkage, those are high risk factors, right? And so we started with a few statistical descriptor, like for numerical value, basically you can get all these statistical distribution, statistical values like a mean, max, mode. And this actually gives you a description about what kind of underlying data is. For example, because we need to ensure, for example, SSN or MIN to be unique for the purpose of transaction, then every single value in that column will be unique, right? Then when you apply this kind of method, you will find the statistical will tell you there are high degree of uniqueness in this data. And then you will see this kind of attribute actually lead to potential risk. So several of these statistic matrix will tell you there is a potential risk this particular field could be a PHI. And then here is our like an overview of the protocol. So we take the data source from various tables, right? Can come with demographic, lab, diagnose, vital, description, imaging report, and then we throw into this like a large bank of feature engineering, and then we come up with all kinds of statistical description on the data. And some of them will tell us the uniqueness, some will tell us the skewness, some will tell us the range, some will tell us if there are certain patterns in the data. Then we generate a sampling technique and then throw into this regular expression to tell us if regular expression find any suspicious patterns from these features. And we combine these two, right? One side from the sampling approach from the regular expression to give us a feeling in the sample obtained from these elements, are there any potential PHIs? And then the other is from the statistical attributes on each column. Are there any general pattern that indicative for this potential being a unique identifier? And then combine these two, we build an ensemble model. So it's a very straightforward, simple model. We just take these two aspects, one from the element-wise, one from the column-wise, assemble them, come up with a final model, make a prediction, and visualize the result for human to make a final judgment to decide whether you want to redact, generalize, or remove those elements, right? So basically, this is the very straightforward high-level PHI detection algorithm. So we have a tabular data. It can be a very long tabular data. I mean, in terms of column, you can have a very wide table. And then a set of regular expression patterns, and these regular expression patterns are pre-given. So we already know a number of potential cases, then this regular expression can be matched. And then we plug in these two models, and then we obtain the probability of number of matched through the template, and then get a probability. And then later we also ensemble this with the classification-based approach. So the second algorithm is taking into account these patterns generated from the statistical distribution. So instead of like treating individual element as one entry, we treat the statistical property as one feature for each column. So each column have more than 30 features represented by these statistical estimates. And then the previous probability obtained from the sampling approach together with this feature engineer-based feature plugging into one single model, then we can use them to jointly predict the probability of each column contains any PHI information. So using this technique, we developed actually a ready-to-use PHI detection algorithm. And then because we expect that this will be used actually on local sites, so we have a database, and then the data, which is CSV file and all these other like extracted table can be jointly read into this local model. And we conduct this profile. Profile means extraction of the column feature, as well as the matching of the sampling on this regular expression. And then we conduct the scan, and the scan is the ensemble model on each column to give a probability of the PHI containment. And finally, we have the report. So this system is compatible on Python, and so you can use Windows or Mac OS. And we build this as a local model because we do not expect that people will use it online because this is local sensitive data. But we do port it a comprehensive data profiler, so that can be connected to various kinds of input from this SQL Acme. So it can be a different SQL portal. And then in the core of the model is just using a straightforward XGBoost library. So this is our interface. So you can select different inputs in the source database. So it's directly connect to your source database or your local CSV file. Using this PostgreSQL or local extraction, we get all the source tables. It can be a lot of source tables, and you select which source table you would like to look at together. So it will screen them one by one and then give you a final report. So you can have like hundreds of tables, but the model will take them all and then look at the sampling distribution of matched regular expression and then a column feature for each of these tables and then tell you the vulnerability. So this is a profiling tool. So basically, once you load it, we'll obtain all the feature distribution and then the feature summary statistic, like I showed earlier. And then we, for demonstration, this is like illustration purpose. We just sample 1,000 records to show you a basic view. But in the actual analysis, we take everything into account to generate the final distribution. Then we use the scan PHI, which calls for our ensemble algorithm to predict the PHI probability. So you can see like the red ones are alarming because we think in terms of combined information, there's a very high likelihood of this entity belong to PHI. So you can see the detected ones like subject ID, date of birth, and then like a date of a hospital, and then some SSN information. All these are identify sensitive ones. So you can use this scan, and then you can check these, and then make a determination whether these things need to be redacted. We provide tools for users to generalize or redact these values. And after this whole process is done, then the user will fulfill this form to ensure there's no PHI is remaining. And upon signing, then the site is ready to commit the data to the data coordination center, which can do a second round of double checking, and then before they go to the NIH Data Hub. So let me show you some experimental result. So we actually extracted real like a structured data from local teaching hospital of 5,000 patients, and then include like more than 1,000 column with 67 of them known to contain PHI. We also did a little bit like a perturbation, so let some column contain partial PHI to see if we can obtain the prediction accurately. And then we engineered a total of 37 statistical value for each column to be served as the feature for input. So you can see like if you directly use a regular expression approach, you get okay performance, but the AORC curve is not perfect. Like sometimes you miss things. Of course, like AORC cannot be perfect on this deterministic approach because it doesn't account all the variation. And surprisingly, like in all methods, like in all 5 folds, we get AOC of 100%. Well, you may think this is overfitted, but this is 5-fold cross-validation. It just demonstrated like this method is very robust in terms of identifying potential PHIs, right? The model is able to rank the high-risk ones higher than the low-risk ones in a consistent manner, no matter how we partition it. And now this is a comparison of the algorithm. You can see like basically ML algorithm alone achieves AOC of 100% already using the 37 features, but Ensemble just gave us another layer of assurance. And then I think because this is just our single site experiment, in reality, I trust like combining these two has benefit, because the case I was saying, there are potential like columns containing partial or PHI, and then Ensemble will give you extra confidence to identify those cases. And I want to provide some explainability. So using the Sharps score to demonstrate like what are the most important features actually being picked by this model to demonstrate like what features actually contribute to the PHI detection. So the number one is gene impurity. So gene impurity basically is to measure the heterogeneity of set of labels. So you can imagine like if every single labels are unique, like a medical ID or MIN, then definitely has a high gene impurity, right? So if you see certain attributes are unique, and then there's like a uniform distributed in the space, and those are very likely to be some kind of identifier for transactional based operations. And then the Bing counts and the Bing edges of the histogram is also important. It depending on the feature, like being categorical or continuous, right? It tells you where is the boundary of these. And the screwiness is also very important. Screwiness is oftentimes related to certain attributes like datetime, floats, or certain values are likely to contain sensitive information because certain like dates are usually not normally distributed in these patient cohort. Then we'll find that screwiness combined with other like impurity matrix will reveal those patterns, and then together we find that this method actually robustly identify all the PHI entities from the data. So finally, I would like to acknowledge this joint work and support from the National Library of Medicine. And then the paper has been accepted by Amy, and we also have it on the GitHub. It's a very simple and straightforward model, but I just want to show you that taking into account the statistical patterns and then the sample-wise matching pattern can be used to recognize potentially sensitive attributes in the data. Thank you. I'm ready for questions.
Awesome. Thank you so much for going through all of that material in a very speedy and efficient manner. So I want to turn it over to my colleagues here to see if anyone has questions. Okay, while folks are thinking, I have a question for you, Dr. Jiang. You mentioned that you know, with this the feature engineering, you're able to make a prediction and provide visualizations of sort of like the risks of how, you know, if there's sensitive information or PHI there. And like you said, you provide those predictions and visualizations, and then humans sort of make the decisions about, you know, what they want to do, right? You mentioned different strategies, like you can generalize or redact. Do you, in what this sort of model provides, do you give any sort of recommendations about like this is, we think because of the nature of this or what the model tells us you really should redact versus generalize? Like how much do you, based on the model outputs, give recommendations to the, to sort of what next steps should be taken?
Yeah, and that's a good point. I think it really depending on the type of the PHI, right? If a date, then we can offer like a shifting or randomization. If it is a zip code, we can offer generalization. If it is certain other attribute, maybe we will just recommend redacting. We'll offer these options, and then, for example, we can recommend one option, and but the user eventually select which is ideal for that data set. Sometimes maybe people want to redact all or replace them with some pre-given token and just remove them. And other cases, they may want to keep some granularity and then maybe generalize them into several bins so that I can still preserve some crude structure. And so I think it's very hard to give like a one unique set of function, but better to give them a set of options so they can choose from. Depending on the category, maybe certain things will not be applicable, but eventual choice is still up to the human.
Great, thank you. We have a question from Henning. Please go ahead.
Hello, thanks for a brilliant talk. You had very impressive validation results towards the end of the talk. Your method, and I guess this was all based on the fivefold validation was based on the same data set ultimately.
That's true, yeah.
Did you, and I assume that the data set came from the same organization. Now, especially in things like coding EHR, and there might be some sort of organizational habits or organizational rules. Have you tried to validate the toolkit against data from another organization to see if there is sort of some, let's say, local knowledge, local habits learned by the model?
Very good point. Indeed, I was thinking because I'm getting data from one single source, but I intentionally get the data from multiple clinics to see whether I can diversify a little bit. But like you said, maybe there are a lot of consistency in the way how they code and put the data together. So right now, this model is also being made available to one of the data generation group in Bridge to AI I'm affiliated with. So there are many centers actually collecting data. And so we're going to test it on a bigger variability of cohort. There may be more than 14 hospitals will contribute data, and then we'll see whether this thing will still work robustly. I mean, I wouldn't believe in my eye, because usually when you see AOC equals to 1, you think something is wrong. Well, tested multiple folds of cross-validation, the result is consistent, and it's not overfitting. What I can say is maybe the data I get is very consistent, so everything is in distribution prediction.
Okay, excellent. Thank you very much.
Thank you. So I think in the future, like I'm also thinking about taking advantage of a large language model to suggest the potential patterns that may be applicable to local. For example, if there's certain features that we observe have a likelihood of leaking information, we could use GPT to generate hypothesis to come up with a hypothetical feature engineered on certain category to be used. And because I can generate many hypothetical feature, and then only the ones that are actually applicable will be retained, right? Then in that sense, I don't have to manually come up with yet another 100 statistical feature. I could use some additional thing to help. I could bring in external information to boost. This kind of thing could be useful if there are strong local typo patterns that are not easily recognizable by the general statistical property.
Okay, great. Thank you. And we have a question from Stephen. Stephen, go ahead, please.
Yeah, hi there. Great talk. Thank you so much, Jiang. The ROC curves you showed are really, really great. Were there false positives? I'm curious what sort of like errors the thing made.
Yeah, because The AUC equals to 1 means there's no false positive, so it's purely accurate in the sense. And this is the task itself maybe not too difficult because there's only 67 columns containing PHI out of over 1,000 columns. So I split them into 5 folds randomly. I ran this multiple times. I always get like AUC equals to 1 in my experiment, showing that the PHIs are actually pretty distinct from non-PHIs, at least on my data set. Like I was saying previously, it could be a fact maybe just because our system coded data pretty consistently. So I didn't see a heterogeneous effect when I was training, and then there's a strong in-distribution prediction. I expect like if I build this model and then run on another site, may not work that well, right? So that's the situation I want to test next.
Great, thank you.
And just to follow up on that, you mentioned that you're working with the other DGPs, and we'll use this with a larger, more varied data set. Do you have a prediction at this point on whether the ensemble model that you showed here is sort of working? It's just as accurate, but do you think that when used on a larger, more varied data set, that the ensemble will be more accurate than either the regex or the ML?
Actually, I think probably the performance will be still very high because just looking at the features being picked by this model, seems they are looking at the uniqueness, right? A lot of the, like I said, the PHI has high degree of uniqueness. So, and then the patterns is different from the non-PHI, and the screwiness or this in combination tells like the 18 identifier actually differs quite a bit from the like non-PHI items. So I expect maybe the model will still generalize decently to the rest of the group, but like I said, like maybe there are some local patterns will influence this model, and then I don't have those information like especially coded for that, and then those could be missed. And then I think maybe we need to think additional feature to be added to accommodate those cases. So the DGP I'm talking about is collecting like data from 14 hospitals, and once they made the data available, then I think we'll test it and see how it goes.
Great, thank you. Any other questions? I know we have to wrap up shortly. There's a question in the chat about if you're able to provide a link to the tools that I mentioned, if they're publicly available.
Oh, yeah. Actually, I have a GitHub link and I will send after the meeting. Yeah.
Okay, great. Fantastic. Well, if there are no other questions, I think we can let you go. And again, thank you so much for a fantastic talk and for sharing with us.
Thank you. Yeah, appreciate it.